Okay, YouTube is back up. So what we missed on YouTube, I think Alex came into the channel and asked if I've tried thinking about this in terms of a system of linear equations. I didn't jump right to trying to turn it into equations. I did go about thinking about Gaussian elimination first, which is a little bit of a dead end because we do want to minimize the answer. Like we want to minimize like a plus b in this case. We don't want just like any answer, and there are many answers. Um, so here we've been brainstorming, and I think we have an approach that might work, right? So here, this is one that's very easy to solve by hand. Um, in particular, thanks to this like 20 right? So that we have one element here that's only influenced by this, which tells me like we need 20 of this button no matter what. So we could solve these by solving uh, progressively easier problems. Just make it easier by removing those. So I'm gonna look at another piece of input, look for edge cases, like maybe that's the only easy one in here, right? So let's look here. Amongst these, is there one that's only hit by one? So, we could programmatically search the input for these kind of cases. So there are 3 7s. There's one, two, there are multiple threes, multiple ones, multiple twos, multiple fours, multiple fives, multiple sixes. And that's all of them. 1, 2, 3, 4, 5, 6, 7. Oh, and there's a 0. Yeah, so this is a case where there's multiples of everything. So I want to look at what solving this one looks like. It's a gnarly one. And then we'll look at how we can do that programmatically. So we have X, Y, Z, W. Let's just use like V, U, V, W, X, T, U, S, T, U. We'll just start numbering these from S. S, E, U, V, W, X, Y, Z. Okay. Now this button, we have a coefficient A, and it is S plus T, UV plus W, um, plus X plus Y plus Z. Okay. And that will continue. But I think we can skip ahead a little bit. Let's just do the B, and then we'll put like a dot dot dot. So B, it's gonna look like a S plus U plus V. And what we want to translate this into is, so we've got an S, and what is it multiplied by? So basically everything that has a 0. So this is A, B, C, D, and F. A plus B plus C plus D plus F. A, B, C, D, F. Okay. Um, equals 215. You know, we don't even need these S's in here. We basically just have the buttons. We're doing the wrong system of equations. We can just interpret this directly into something else. So A plus B plus C plus D plus F equals 215. Don't need that S in there. And then all the ones, everything with 1 adds up to 215. So A plus, so A, B, no, A, C, D, E, F. A, C, D, E, F. And if we can solve this by hand, then we know we can do it programmatically. And I'm just going to put in gaps here to make it more obvious. So this also adds up to 215. Next line is going to add up to 28. So 0, 1, 2, everything with the 2's. In this case, that's a, no. B, C, D, F. B, C, D, F. That's very constraining right there. Good. Now this one adds up to 19. So for 19, 0, 1, 2, 3. This is the 3's. So B, C, D. It's just B, C, D. B plus C plus D equals 19. And looking at these two, that gives us an F. But let's just lay it all out. We have something that adds up to 198. 198. One, two, three, four. Wait, no. 0, 1, 2, 3, 4. So everything with the 4, that's A, E. Okay, A plus E. Okay, and then you have a 2, 4. And that's everything with 5. So that's A, C, F. A plus C plus F. And then this 204 is adding up to a 6, or everything with a 6. So A, C, D. I should have picked a smaller example. I'm sorry, this can't be the most fun to watch. We type these out. A, C, D, and F. But having a big example can help me find all my edge cases, right? So that's the goal here. And then everything with a 7. So that's A, C, F. A plus C plus F. Oh, that's interesting. These two are always together. So 5 and 7 are always together. 5, 7, 5, 7, 5, 7. Cool. Okay. Now, what can we get from this system of equations? Um, where are some obvious bits? So this one here, right? If we plug one into the other, that implies that F equals 28 minus 19, which is 9. Mhm. And can we plug F into any others? We can do these in separate lines so we share our full thought process. Um, I mean, I suppose we could just subtract 9 from everything. But is there anything that just uses... Okay, well, these three are interesting in that this seems to imply that D is just 0, right? So 6 is everywhere 5 appears, and then also in one more time in here. So that makes D equals 0. And again, I guess we could just say we subtracted one from another. We subtracted one equation from the other to get there. So we're kind of doing Gaussian elimination-ish stuff. Um, okay, what's the one that gave us F equals 9? This one implies F equals 9. Okay, now if D is 0, then which of these? So B plus C then is 19. That might be helpful. We still have A plus C plus F is 204. Now these two have a lot in common. Is this to say E and B are both 0? Or rather B plus E is going to be 0? But you don't have negatives, which means they're both 0. So B plus E equals 0, which no negatives implies that B equals 0, E equals 0. Or was it B minus E equals 0? Hold on. We subtract, let's say we subtract this line from the other. We have B minus E. B minus E equals 0. Or rather, B equals E. Oh, right. That's what we're getting. That's what we're getting at. Because we have to have these in equal parts. The number of times that this button is hit is the same number of times the E button is hit. So B is hit the same number of times as E, 1, 4. And that's necessary because of the two 15s that say 1 and 2 need to be hit the same number of times. Yeah, right. The two 15s constrain this so that anytime we hit the thing that increments the 0, we need to hit the thing that increments to 1 in the other one. Mm. Okay. We might need to take tomorrow afternoon and do some math here. Or like do math in code. Maybe I'll sneak in some cleanup before then. Skip over some of the boring part. But hold on. So B and E are the same. Let's at least finish this thing. So if E is the same as B, A equals AB, sure. These two are kind of useless now. B plus C is 19. Wait, we don't have a B equals 0. We had B equals E. So like C plus E is 19 too. If I can't solve this by hand, I can't expect to get a computer to do it. You've got some similar equations. You were thinking about starting from the jolted for the smallest number of counters and then pruning it. Yeah, I had that thought too. But where do you go from there, and how do you make sure you don't like back yourself? This feels like a linear algebra trap. The example has 3 different types of systems of equations. I see Black Deep. I'm sure you've solved this by now. Did you use a library? Did you do linear algebra for this? You only did part 1. um, I am running out of brain power. The last thing I want to do is just solve this equation by hand. I could plug stuff in. I could simplify some of these. So f is 9. We have a plus c plus f. So we have what, a plus c equals 195. And we have A plus E equals 198, right? So um, we can subtract one from the other. We have C minus E equals, or let's do it the other way around. So we have E minus C equals 3, or rather, E equals C plus 3. Um, Great. What else can I work with? Let's collect what we know. Um, B, so B equals E. Um, E equals C plus 3. F equals 9. D equals 0. A, B, C, D, D equals 0. You're trying, but you can't get there. These don't have an exact solution, so it's not just plug and play matrix algebra. Yeah, so you can't just use Gaussian elimination because there are many solutions, and what you have to find is the one that minimizes the sum of the coefficients. Um, it is kind of tricky because I'm not sure which ones are actually the variables. So like there's this way of expressing it, where these are the coefficients, but maybe actually these are, I'm not sure. Your best idea is to start with the equation with the fewest variables, generate all possible solutions to that, and then go through each following equation with those possibilities as constraints. Yeah, so just do kind of a smart search through it. But their inputs were the fewest variables and an equation is 5. Yeah, I thought about doing that, and then I started looking through the inputs, and I saw stuff that was scary for that. But I mean, I guess you could do that for the ones for which it works. Like take the shortcut if you can, and then otherwise just search the long way. I mean, I think any given equation I could solve. So if I were to do this for, do this for the problem set, and oh, let's do the one we're working on, which is line 1, 2, 3, line 3. Yeah. Whoops. So we're gonna drop to list dot drop 2 dot take 1. And the answer here, oh, I thought it'd be fast for that. We're only solving one line. So this is my former what do you call this? Dijkstra approach. And wow, that's slow even for that. Okay, I take that back. Mm, let's try a YOLO. I think we can do a YOLO for 1, right? Uh, get lines that drop to to list dot take 1. Or we can do drop to dot take 1 dot to list. There we go. And we'll let that run. We'll let that run the Dijkstra for just 1. And once we have an answer, we'll also print this sum. Um, What was my approach for part one? Um, oh, it was pretty dumb. Or like by dumb, I mean like not doing anything clever. It's not in here. It's in the worksheet. Okay, give me a sec. I'm just gonna get this YOLO running. SPT run main 2025 dot day 10. Okay, we'll get that running. And we have day 10 worksheet. Use a breath for search. Um, so my search strategy for part one was brute force, but with some smart. We chose a number of buttons, right? So we start with we look at all the indices of buttons. So we start with 1, 2, 3 and for each of those numbers of buttons, we just get all the combinations of that many buttons, and then we reduce. We press all the buttons, and I had converted them to binary. Um, so in this case, my buttons were all like integers, and I just reduced them with XOR, and we checked if that matched the goal. So if there existed any combination of that number of buttons, then I would return that number of buttons. Yeah. So I checked all subsets, but I started with I started with the small subsets, and that ran pretty instantly. Okay, let's check on this. Wow, this is for one line. I thought for one line, this would at least be fine. But what is that line goes deep. It goes to 204. And by the time you get to 204, you're doing I mean, there are just so many ways to get to 204 presses of any button, right? When you have that many buttons to choose from. Oh, and you know what? Here in my search, hold on. I think I do want to improve this. So in my search here, I try pressing all the buttons. So we get to the same path in multiple ways. We need to I mean we do dedupe, right? Are we deduping? So we press all the possible buttons from here. And if not, class that contains S. Right. So this is a map. That combination of button presses is a key. So that is deduped. I can't help but think there's a smarter way to go about that. Yeah, there's probably a smarter way to go about that, but it does at least dedupe, I think. Maybe I should be printing those. I mean, we had some of these in Scratch, right? Like here, you can see the search strategy happening. Um, and to find like the first one in the example, it takes a few hundred. That feels like too many. That is too many. Okay, so my Dijkstra search isn't even a good Dijkstra search, actually. So I'm gonna have to revisit that. You also converted them to binary. Yeah, it was silly. I mean, maybe it wasn't silly. Like it is easier to write XOR than it is to like zip those together and do the whole, I don't know. But also I was secretly hoping that it would make part two easier. And it didn't. It didn't matter. This is not Go. This language here is Scala. Okay, yeah, we have a bad search strategy there. So if we want our YOLO to work, we're not gonna let that run. I mean, we did find it after 1,000, but 1,000 is too many, especially when you're just doing, 23 button presses. Wait, are there 1,000 ways to get? Let me think. Let's go look at the example. You have a choice of four buttons, right? For the first one. No, no, no. For the first one, you have a choice of one, two, three, four, five, six buttons. So if you're gonna get 10 button presses, six choices for the first one. Okay, like this is kind of 6 to the 10th, except that again, the button presses are commutative. So like once you can, and we are deduping, but we are looking at way too many dedupes because each time we're multiplying our states by 7, and then like we dedupe, but still we shouldn't be doing that much deduping. So we need like we do need a smarter search strategy even for our Dijkstra. Um, it still worked for part one for the example. What if we generate all valid states for X presses starting from 1? Um, for the first example, the BFS test 39905 button presses. um, but this is for all three of these. Generate all valid states for X button presses, for X presses. Yeah, okay, that might be smarter. Right? Because then we could just do like number of ways to sum to a number, right? And then how many ways are there? So like and where is my whiteboard? So when we're choosing like some number, enable sync, refresh. Let's refresh that. You need at least Y presses where Y is the smallest number in the joltage list. Yeah, so you can start your search there. And I just want to do like the combinatorics accounting of this. Um, so we press one button like some number of times, right? And then we do a boundary. We press another button some number of times. Let's say there's 4 buttons. And then we press the last button once. Um, so this would be, we just need to choose, we have this many positions, and we're choosing 4 of them, or 3 of them to be boundaries. So this is the, what is it, number of presses. So let's say n is the number of presses, and then b is the number of buttons. So let's just give this a number. Let's say it's 20. So this would be 23, choose 3. choose three indices to be the boundaries. And that's not bad if you know, b minus one. Wait, b minus one. Eh. So if that's supposed to be a three. So if b maxes out at what, 10, then this starts to get to be, oh, this can start to be 23 choose 10. So maybe that's a no-go because we're doing this like we guess maybe we'll need 23 presses. But if we need like that many boundaries, then this is getting very big because these are factorials, right? Yeah. It was worse doing the math. Um, I don't know. Like, I used to be a math kid. I shouldn't be so scared of doing doing the math before trying to code. It'd save me a lot of time. Max button presses could be approximate sum of jolts. Yeah. But then like even if we started there and then we optimized, like we improved our answer by decreasing some button press and like increasing some others, right? And looked around that state. So like we approximated and then we keep trying to improve our approximation. I feel like something like that could work, but you have to be really careful about the implementation. Um, and again, even if we just started with that button presses, there are like a lot of combinations to try, right? How many ways are there? Like we add up all the joltages together. There are many different ways to choose between 10 buttons, to choose different amounts of 10 buttons to get there. So I think we need to do something smarter that looks sort of like solving it by hand. Right? So something like this. Like I feel like I'm making progress here. And if I could figure out like what the mechanism is here and just generalize that. I don't know. I should read a book on linear programming. I could really use that. And it's been a long time since I've done like a linear algebra class. And I've just never done anything like computation wise. So that could be a that could be a new year goal. Next year I'll be prepared for things like this. Um, I know there are like linear programming classes on Coursera or something. Maybe I could do something like that. I feel like it would help, right? So, what's the closest thing to being determined? We have D, we have F. A is pretty close. Um, right, whatever E is, it is C plus 3. Yeah, these two equations. Oh, hold on. I think we did our C and E wrong. A plus C. Oh yeah, A plus C plus F is that. Yeah, the info to solve for A in the first line. Um, Do I? I can solve for A here. Let me see. A plus all that stuff. Oh, right, between these two. So this bit here is equal to 28. So thank you for that. A equals 215 minus 28. So then A equals 285 plus 2, 287. Put this down here. Okay, A, B, we need C and E. Let's put these in order. A, B, C, D, E, F. Oh, and at this point, we just take like A plus E. So if 287 plus E, so 287 plus E equals 198. Then E equals those two added. So 287 plus 198. E equals 485. E equals 485, which means C is 3 less than that. C equals 482. 482. A, B, C, D, E, F. Were there only 6 buttons? 187. 187. Oh, yes, you're right there. That changes the math of other bits. I think these two just both go down by 1, right? Because 187 plus E equals 198. Oh, so E is, what, 11? If E is 11, C is 8. Oh boy. And then B is also 11. Yeah, I added instead of subtracting. Okay. Does that math look correct now? 187. Let's just plug these in. So try this line. So 11 plus, I'm going to define these. We'll comment those. We're just going to do these in Scala code. Val, all of those. And then we're also going to uncomment these. And put a comment here. Okay, let's see if we get those numbers. A10 has been rough. We're solving things by hand, and then hoping we can figure out how to generalize that. Some sort of linear optimization problem. Okay. Well, cool. Things are matching the comments. So we know you have the right values. Maybe down to me. Oh man, are people giving up? I still have to shape some loaves before I go to bed. So I bake bread, um, and I've had some dough that's been rising, and I'm gonna shape the loaves, put it in the fridge. Then when I wake up at like noon tomorrow, I'm gonna put it in the oven. Try LP. Yeah, okay. I need to try LP. You're right. You're right. Um, but I also maybe need to sleep on this. And the question is, do I do this in the afternoon tomorrow? Okay, I feel like if I think on it and I know exactly what I'm doing, I could do this in the hour before the problem drops tomorrow night. So I could log on an hour early and get it done, just the implementation part. Everyone else is tapping out. It better not be knapsack DP. What is knapsack DP? The my bread recipe. Well, that's confident. The confidence is just in my. This feels like something I could. If I know what to do, I can code it up. So that's if I think I know what to do. It's just the problem solving part I need to get out of the way. No, I've not heard of that. I learned bread making from the book Flour, Water, Salt, Yeast. Um, and I even visited that guy's bakery in Portland, Oregon. It was a popular book on bookshelves for a while. Let me look up knapsack DP just in case. Knapsack problem. Oh, okay, yeah, I guess it is kind of a knapsack problem. Which book should be maybe. Yeah, I think I just need to do some reading before I continue this because sometimes sometimes I just go flying blind. Um, Especially when you're kind of just doing it live. Like you don't want to stop and think for too long. I know sometimes I'm afraid to stop and think about the problem before trying a solution, and that can get you down some weird rabbit holes. Yeah, we finally got our hard day. Everyone on Reddit's been complaining about problems being too easy. Yeah, this is legitimately a tricky one. This feels as hard as as some like near last day problems. This feels like a day, 20 plus for sure. Um, I think there's no point in trying to optimize this. We're just gonna go with an algebraic approach. Yesterday, part two wasn't bad once you got to the once you had your light bulb moment, or for me at least, my light bulb moment worked really well there. Yeah, I think I'm gonna table day 10 for now, but I wrote a blog post for day 9. Would anyone like to see it? Because let me see. I think it cleaned up really well. I think I did a good job of making the problem look really simple. Okay. Oh, wow. Is something running? I know things are just feeling slow. Okay. So for day 9, this is my approach. So basically we use oh, nope. What happened to the markdown preview? Okay, so basically we use rectangular representations to search all the rectangles, do brute force, and then in filter 2, so in part 2, we just filter those rectangles by checking if there are any boundary intersections, any intersections with boundary lines. So part 1, I won't read the whole thing to you. Eventually, it'll be a blog post. I'll link it in Discord. I'll drop the link here in chat. It's not live yet. It's under review. But basically, we parse into a point and an array. So an array, I mentioned, I'm basically using like this is basically the 2D analog of a range, right? It's not an actual grid. It's not an actual 2D array, just like a range is not an actual array of integers. It just represents that range of integers. So you can represent a rectangle by using two ranges of integers. And you only need 2 points to create like a bounding array. So we use those 2 points to get all possible rectangles. And for each of those, we calculate the size by taking the sizes of the individual ranges and multiplying them, right? It does go with everything. You're right. Um, so part 2. Um, this is, I think, where my approach was able to simplify things nicely. So there's only a single constraint, and that's the rectangle must be wholly contained inside of the whole drawing, inside the whole shape that we're creating with all these boundaries, right? And my insight here was that for if any rectangle has none of those boundaries crossing through it, then it's going to be all one color. And that could be outside of the shape, it could be inside of the shape. But as it happens, here, let me show you this image here. Someone generated an image of, yeah. As it happens, this is what our input looks like. It's a big circle. So we don't have to worry about these rectangles that appear outside here. We can just look at these that are inside. Um, so what I do here is I also represent each of those lines as an area, as a like a tiny skinny rectangle. And now all I have to do to check that a rectangle is green is check if it intersects with the other with any of those smaller skinny rectangles, right? Any of those boundary points. And here I thought this intersect method was defined nicely. So to check if two areas intersect, I just check if either their x ranges intersect, or I check that their x ranges intersect and that their y ranges intersect. So if their individual ranges intersect, then the areas themselves intersect. And checking that two ranges intersect is also pretty simple. Either one range contains the minimum of the other, or the other contains the minimum of the first one. So a very simple check here, and this is all a constant time check for overlaps. That's expressed, I think, in a nice way. Then that lets us write this all green function. So we just check all of our lines, and we check if any of them intersect with our area. And that's what we need to use in a filter. And our part two answer is just this. So we get all the rectangles, we filter that they're all green, map to the size, and get max. So the final code is just this. So this is without my library dependencies, and it's not too long. So here's the area. It has a definition for. Oh, I skipped a bit over like doing the inner area, but that's like a little edge case thing. Um, Size, inner, intersection, and then construction of an area. Then my part one and part two code can be very, very short, just a few lines for each of them. Um, how do you know if it's out or in? Yeah, so I skip over that. And I mention, so this article also does mention the edge cases. So there are edge cases that don't need to be handled. Um, and that's because of the shape of the input data. It's a circle, right? Um, and then there's another edge case. So I describe it here. It's where maybe I could draw it too. So let's say we have a square, but it goes like this. So here, there's a boundary that's crossing into our rectangle, but if there's nothing here, if this is like there's no white tiles in here, right? This can all just be green tiles. So I don't handle that edge case, and I don't handle the case of rectangles on the outside. So this would match my filter, but it's going to be much smaller than whatever this thing is here. So those edge cases don't need to be handled. And then I make a note on like various optimizations you can use. Yeah, it can be very convoluted. Um, so like I saw code from another guy that did handle those edge cases, and it's not worth it. It's not worth it. It's a lot of work. What you like about this is the low labor, but you're curious if anyone that knows more involved ways to make bread. Oh, you're talking about the bread recipe. Can make it a serious recipe, or would like the result of the easy recipe. I don't know. I like I like that is 24 hours and that you give it time to ferment. I think that's the most important thing in bread making is that you give it time to develop. There are like 2 3 hour bread recipes where you just like throw in a bunch of yeast and let it expand, and it just doesn't have as much flavor. So with bread, less yeast is better. Less yeast, more time, you get more flavor. So even if it's low effort, it's a good recipe if it's a long time. You're still working on your coordinate compression approach? Yeah, I started going down that. um, oh boy. Yeah, I was hoping it would be quick to implement. I like I like how potentially clean coordinate compression could be and potentially fast it could be, but this approach here is just faster or like to implement. Like once I got that, it was a few lines of code referencing my library methods I already had. Yeah, so when this is live, I will send that link. Um, I'm gonna call it a night. I'm gonna do some reading, do some thinking on this puzzle, and when I log on next, maybe tomorrow afternoon, maybe tomorrow right before the problem, then I will finish off part two. You added a depth border around the outside of the shape, then checked if any of the sides of the proposed rectangle insert intersect with any of those points. Oh, okay, yeah. Makes sense. You didn't need to, but it works. Um, I have a Discord, by the way. Um, if you're trying to find me at times that are not Evan a code, there's that. I'll probably mention it on Discord if I'm logging on at a weird time. And let's see if there's another straggler. Maybe there's no stragglers, but maybe like some of the Europeans woke up and are working on Advent now, and they haven't yet given up. I do like that idea. I gotta get my bread going. Liquid cake just started. Okay, I can follow your recommendation for sure. Let me make sure I'm spelling. I don't know why this is taking so long to load. Someone's doing functional. Oh, in Erlang. Cool. Yeah, I'm down for functional. I can leave it to Sorcerer to find all the functional programmers. That's Liquid Cake 1. All right. Slash raid liquid cake 1. All right. Well, thanks for sticking around. This is a gnarly problem. Oh boy, but we got one line of it solved. We did one line by hand. FP for sure. All right. Have a good night. We'll solve this another time. We gave it a good shot.
Okay. Oh, so these buttons are wired to lights, I guess. Um, 034 means you toggle the first, fourth, and fifth. Yeah, okay, fine. Because none of the machines are running, the jolted requirements are irrelevant. I see that's part 2. You can push each button as many times as you like. However, to save on time, you need to determine the fewest total presses required to correctly configure all indicator lights for your machines in the list. For all machines in the list. There are a few ways to correctly configure the first machine. You push the first button 3 times. Push 1, 3. Okay, I see where this is going. The second machine... So basically, this is solving the the flippy cross puzzle, except it's not a flippy cross. I actually don't know how you solve the flippy cross puzzle. All I do when I'm given one of those in a game is I just mash. So that's Lights Out. Yeah, that's the guy. Although it's not the Simon Tatham Lights Out, I think. Is this? Oh, it's Light Up. He calls it, which is this game with directions. So it's the opposite of Lights Out, but that's also not the same game. Right, anyway. I guess we have to mash, yeah. So we need to know how to read the input file, which I can't remember how to do. I think there's like file read or something. File... What can we do? We can read. We've got a sample. We can fill sample. That was not the expected paste. What happened there? Thank you. So we file read sample. And what happens? Undefined function file read. That's interesting because it totally does exist. IO device number. That doesn't look right. File read file. Okay, that looks good. That's what we're doing. So we file, read, file, file name. And this is going to be raw, I guess, something like this. We're in for so much fun, apparently. Well,